Right, so in this lecture we want to talk about electrophilic addition to alkenes. Specifically, we're going to be looking at Mecurinium and Halonium intermediates. These are the three-membered intermediates that have a sort of positive charge on them in terms of reacting with alkenes. To start off though, I want to just look at an example of a hydration of an alkene. Now, under the kind of Markovnikov mentality, I've kind of mentioned before, like this would be a great reaction, being kind of taking an acid, protonating it, you get a carbocation, and then what you want is you want the nucleophile to be water, and you want water to be able to come in. So the idea here, of course, is that the pi bond attacks the proton. You get it to say, there's probably be a carbocation over there, it doesn't matter which side it forms on. And then you got this water that comes in and it protonates and we get this water. Now, this is taught. I've certainly taught it for many years as well as a type of a reaction that can occur on alkenes. And the simple answer to this is for better and worse, this is pretty much a lie. This type of reaction doesn't work very well at all. And if you go into the literature, you really just won't see any examples that look like this. Very, 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 very few. The problem is, of course, is that the conditions that we would use in order to add water to a double bond are exactly the same conditions that would cause the water to eliminate and to form an alkene. So the problem is this as a reagent is not really good. Now, there are many other ways to achieve the addition of water over a double bond. Now, what I want to show you now is one way which is also terrible. Hardly everyone uses it, but it leads us into some principles which really come out in the halonium intermediates, and that's why I want us to just look at it. So the reagents that we use, and this is why no one uses it, it's mercury, all right? Yes, mercury, that can kill you. Mercury acetate, it's not something you want to work. You don't really want to be doing this reaction on the ton scale. But it is a reaction that works, and we can look at how. So, this ends up being quite a bit of a two-step reaction. We're going to be using this mercury, and generally it's the diacetate, mercury diacetate, as two-step, and we need to do it in the presence of water. Typically there's a co-solvent of THF, that's really the solvent because we need something to kind of solvate things. And then there's a second step which is really important because of the intermediate, and we have to do that mechanism now to actually understand what's going on. So normally as a second step we need to add sodium borohydride. Okay, so how does this react? Well, the key thing here is the mercury. Mercury is 2+ at the moment, and like most metals, they're very Lewis acidic. And we've got this weak nucleophile in the pi bond, which adds to the mercury like that, and it kicks away one of the acetate. So our mercury is kind of our acid, just like in this first reaction, the H+ would have been the acid. And the intermediate that we get is a three-membered ring. So just remember that we lost one of the acetates. That's the type of leaving group that left. And the mercury has bonded on and we formed this three-membered ring. Now, the reason that this can happen is that mercury is a really big atom. And so whilst it will accept the electrons to the mercury metal, it also has lone pairs which it can back donate onto the carbocation. So one of these carbons would have been sort of carbocationic. When we draw something like this out, we've got this, for me this is fine and helpful to know that because this mercury is positively charged, we effectively have two sort of carbon-mercury bonds which are very weak, and we want to get those electrons back onto the mercury. So these are effectively good leaving groups. So if we've got a nucleophile present, and in this case we've got water that is present, and water is a much more better nucleophile than the acetate that was given off, and certainly there's a whole lot more water that is present. So what can happen here is that the water can then act as a nucleophile. It adds to either side of that and it kicks open the mercury like that. And so what we end up with is a molecule. It's basically an organometallic, where we've got that's Hg, O acetate, plus we've added on our water. Now we mustn't forget, of course, that the water is now positively charged. So our water was the the nucleophile in this place, often color nucleophiles in blue. And we still have our Lewis acid here in terms of the mercury, this metal. So a carbon metal bond is going to be very weak. And it turns out the best way of kind of removing that carbon metal bond over there is to use a reducing agent like sodium borohydride. And that's why we need the second step. So step one was the formation of this intermediate. Of course, what needs to happen as well, I haven't shown this, but the H plus can leave from there. In fact, it can just go and form acetic acid. We've got the counter ion over there. Not a strong base, but strong enough to certainly pick up this proton that is over there, which has a much lower pKa because it's oxonium. So we'll get the alcohol, sodium borohydride reduces this and puts one of its H's onto that carbon over there. And so what we end up with is our alcohol like that. Okay, I want to take another little, slightly deeper dive into what's happening over here, because what we're going to deal with is going to have direct implications for the halonium. So we might as well use this as an example, get the most out of what we're teaching over here, because it is a method, and certainly if you write this in an exam, this is a method of doing a hydration. But what I haven't shown you here is I've used a very simple alkene, and this simple alkene is symmetrical. It really doesn't matter which side the water adds to, it just adds to one of the sides. So let's just see what happens if we don't have a symmetrical one, what happens. So let me take, just to be slightly different, use this simple alkene over here. And I'm going to do the first step, which is the treatment with our mercury acetate. So we've got two of those over there, and we've got our water. So this is the reaction we're going to add there. I really should have drawn in two bonds. I could have shown the acetate leaving. Bad me, but let's not worry about that. And so what we end up with now is this Mecurinium, charged intermediate. And now the question is what do we think is going to happen when we add the water that is present here? So there are two possibilities that could happen, and we're going to look at the product to actually work out what the real answer to that is. So the first possibility is that it goes to this carbon over here. Now, if it went to this carbon over here, our argument that we'd use is that this intermediate over here is a really stable type of intermediate, and the nucleophile, because that's what this is over here, it's a nucleophile, the nucleophile wants to go to the least sterically hindered carbon over here. So that would be a good argument if the water ended up at this point over here. But what if the water ended up on this carbon over here, which is more sterically hindered? So then our argument can't be that it wants to go over here because of sterics. That's completely unusual. But if it did end up over here, how would we argue that? Well, a way to argue that would be to say, well, actually, what's happening over here is that this is a very unstable sort of intermediate. It's positively charged mercury. And so there's kind of like either a slight positive charge over here or a slight positive charge over here. Now over here, a slight positive charge would be a secondary type of carbocation, and over here it would be a primary carbocation. So if the water goes to this position over here, our thinking would be that this is probably because this over here is more of a secondary carbocation versus this one over here. And so this bond, this side of the bond, is slightly weaker than this side over there. And that turns out to be what happens. The Oxymercuration reaction, this is the addition of water using mercury, does go to the most hindered side overall. So I'm just going to draw out this intermediate and we can stop at that point, because the next step would be to reduce with sodium borohydride so that we ended up with just effectively water adding over that double bond in that way over there. And so this is an important principle. It's going to come up now with the haloniums, which are far more important. Synthetically, the next ones that we're going to do now are extremely important. But this leads us into just some of the background ideas that are going to come up with the halonium, so I don't have to explain them again. So the idea here is that this three-membered transition state that's happened over here, we can't isolate it, it's extremely unstable, positively charged. What happens is that we really have very weak bonds here, but this bond is slightly weaker because the developing positive charge that's over there is more stable than if it was on that side over there. And that gives us a clear indication in terms of why the nucleophile wants to come to that position over there. And we're going to see exactly the same thing with the haloniums. So now we need to talk about the halonium intermediates. And in the introduction to electrophilic substitutions at alkenes, I explained to you, I gave this example of bromine and how an alkene will very nicely add to a bromine and kick out a leaving group. But bromine is extremely powerful electrophile, just molecular bromine, extremely reactive because it's got this really good leaving group on it, and you just need a slight little bit of a hint at a nucleophile wanting to approach it, and all the electron density goes to one side of the molecule, and we get this, effectively it's like kind of like a Br plus and a Br minus next door to each other, and so we get this induced dipole as the nucleophile adds in. This pops off because it's such a fantastic leaving group. And so these reactions are typically done just, you can do this at room temperature, but you can even do it at very low temperatures like 0 degrees Celsius. This will work absolutely fine. Typically dichloromethane or a halogenated solvent is used. That's not too important in terms of the context of this course. So what we have here is, the one is the powerful electrophile, the other one is that leaving group, and we get our bromonium intermediate. Now, this bromonium intermediate has exactly the same thing as we looked at with the Mecurinium intermediate, and that is that when a nucleophile wants to come in, this being the bromine atom, which was the leaving group, it now becomes the nucleophile. Where it wants to attack is at the most substituted carbon over there, because this is an unstable species over here. And so the bromine does not want to form two bonds. We don't see bromine forming two bonds normally. It's always, one bond to bromine. That's how the halogen should work. The only reason that this thing over here exists is because bromine is really big. So when it forms the bond, it accepts the electrons from the pi bond shared between the two carbon atoms. The bromine has another set of lone pairs, and which can sort of just, in a sense, kind of flop over just to stabilize the charge on either of those atoms. And if you think about it, which carbon is it going to most want to stabilize? Well, this one over here would be a probably carbocation, so that's going to be the strongest bond. Whereas this is a secondary carbocation over here, so this will be the weaker of the two bonds because it's the one that it's sort of trying to stabilize, the weaker one overall. So that means that the nucleophile wants to come in from the most substituted side, and we get this product over here. Okay, you might say to me, hang on, Prof, this it seems a bit silly. How do you know that this bromine over here was the one that was given off in the leaving group who came in? And how do you know this one was the original electrophile? Because, to be honest, if I got this product over here, they would be exactly the same thing. You would have no way of, they're both bromine, so you would have no way of knowing which one was which. So the answer to that is not actually directly from this reaction, but rather, one of the most powerful things of why we use these halonium intermediates. By the way, bromine is the most common. And so pretty much all my examples are going to be based on bromine. We're going to just focus on that. But you can use chlorine, not as effectively. So you see some cases of that sometimes. It's fairly rare. But iodine is also one which is used in these types of reactions. And iodonium is also really, so if you see iodine being used instead of bromine, you shouldn't be afraid. It's exactly the same thing. It's just with iodine. I don't like showing iodine because the abbreviation of iodine is just a line and then it looks a bit weird. So bromine is just a nice one to use and is the most common version. So the most important thing about these halonium intermediates, this bromonium intermediate that we have over here, is let's do the reaction with a better nucleophile present. Br minus is not a good nucleophile. But if we have a better nucleophile present, for instance, we did this reaction with bromine in the presence of water, all right? When we're doing it in water, we kind of need some solvent which is going to help with the water and dissolve things. So THF is a good one. You could probably use DCM as well at the interface. But then what happens is that when we get our bromonium intermediate, so I'll draw it out here, we do have the Br minus still present, but we also have water present. And water is a much better nucleophile than Br minus. We should realize that. Remember, what's the better leaving group? Br minus is the better leaving group. It's the more stable conjugate base. So water is the one that's going to attack, just like we saw with the Mecurinium intermediates, and we are going to add water over there. And last but not least, we can just remove that proton over there. It can come off into the solution. It can protonate the water there. We will probably work up this reaction. Well, I don't want to talk about the workup, but there would be some form of base to kind of mop up the acid that is formed over there. But we're going to lose an H plus and generate our product over here. Overall, this is a really important step to be able to do, and this comes up in many different ways. So I'll show you one possible feature of this, which is quite nice. But this generally goes under the name of halohydration reaction. So halohydration, because we've got halogen and we have added water. So there's the hydration part of this. So a halohydration reaction is a really important reaction of alkenes. And we could use any nucleophile over here. So we mustn't be too scared about that. There's a lot of different varieties of nucleophiles we can use. A very common one is water, but we could have used an alcohol, we could have used a thiol, we could have used many other sort of nucleophiles. But anything that's better than Br minus is going to be the nucleophile and add there. And so it is quite important. Something that's quite useful with this type of reaction over here is actually if we treat this over here with a very strong base, irreversible base like sodium hydride. So sodium hydride is a nice strong base, and the most acidic proton over here, because this is a pKa, the proton form of H minus would be a pKa of about 33, and this one has a pKa of 16. The base can deprotonate that, and it makes an O minus. And when it makes an O minus, you now have a molecule that has both a leaving group and a nucleophile. So I'm going to change the bromine now into a leaving group like that. And we've got a very good nucleophile in the form of an O minus. And what can happen is this can kick in like that and kick out the bromine, and we form an epoxide. And in the next lecture, we're going to look at ways of making epoxides directly from alkenes. We've got some great ways of doing that. And we're going to look at the reactions of alkenes. There's a few more things that I need to say about this. So let's just continue to some special things. We need to talk about this over here. The principle that we're seeing over here is the regioselectivity of how the opening of the brominium happens. So this is regioselectivity. But we also need to look at stereoselectivity and just another reagent, which is much better than just adding pure bromine. So let's discuss that now. Now, I have no doubt that those of you who are looking at this have never actually worked with molecular bromine. We need to understand that molecular bromine is a terrible, terrible thing to work with. It is not fun. It is a liquid, but it's a brown liquid. It means that it's very difficult to measure out if you're using a syringe to try and measure and see where that line is, the meniscus, to try and get everything correct. It's extremely difficult. And one of the things they don't tell you until you actually do this is that when you work with molecular bromine and you take your syringe, you stick it into the molecular bromine and you suck it up, you need to work very quickly, because what you'll notice is very quickly the stainless steel on the tip of the needle that actually got exposed to the bromine very quickly starts to rust and react. And so it's not a nice reagent to work with. In many cases you do have to do it, but there is a far nicer one, and it's called NBS, and it stands for N-bromosuccinimide. That's not really going to help you too much. It's perhaps good to just draw out the structure of this reagent, so you've got an idea what it looks like. All right, so this is N-bromosuccinimide. Now, we don't actually, you can go look in your textbook. We don't need to know like the mechanism of precisely how this thing works. Only to just know that N-bromosuccinimide essentially breaks down to give Br2. All right. Under weakly acidic conditions, it's normally you need a bit of acid present. There's enough to, in a standard reaction, just enough to kind of get that going. So very slowly this breaks down. It is a slow process. And this is the key thing here, is that we can take N-bromosuccinimide and it will gently produce Br2, which is very, very powerful, but in a very slow manner, which means that we have a lot more control. But there's another cool thing. This thing over here is a white powder for all intents and purposes. It's actually very crystalline, but it's essentially a white solid that you can easily measure out. You can weigh this out. You can actually recrystallize this from water. That's how kind of stable it is. Normally, organic molecules in water are terrible, but you recrystallize it from water. You can dry it. And working with NBS is just so much better than working with molecular bromine. So it really is important to recognize this most often, almost always. Well, in your case, it will be this, is that it's going to be abbreviated as NBS. And you must be able to recognize that that is the reagent that generates out the bromine that is present. So the next thing that we need to look at is stereoselectivity. So to explain this, I'm going to just bring in our NBS over here and bring in our water. So we're going to be doing, this is the form of bromine that we're going to use. So we're going to do this Halohydration reaction again. And I'm just going to use, this is just really a nice example, is to use a cyclohexene unsymmetrical so that we can see how all these things work. So what happens here is we generate the bromine and we're going to get our brominium intermediate. And I'm going to make a slight variation now to some of the other structures that I've drawn out so far by showing some stereochemistry that is evolving in this reaction. So what I haven't shown you yet, but hopefully this is something that makes kind of complete sense to you, is that when the bromonium forms, it must form, it's adding to one face of the alkene. Now this molecule has no stereochemistry in it whatsoever. And so when the bromonium forms, it's going to either come in from the top face or it's going to come in from the bottom face, from underneath. And both of those options are possible. But what's not possible is where the bromonium forms where the one bond is going up and the other one is going down. That is just geometrically completely impossible for a three-membered ring to form like that. So what I've done over here is we've got to take with a pinch of salt here. We've got to be very careful. This I'm showing is actually one enantiomer because I'm showing the bromine pointing on the top face, the bromonium being on the top face, and the methyl group having therefore gone down because the bromine came in from the top, so the methyl group must be going down. So we need to remember that this is actually racemic, all right? There's nothing that told us whether the bromine was on the top or the bottom. Okay. However, in the next step, the water needs to come in. So we've got our water, it's lone pairs of electrons. And in terms of regioselectivity, we know that the water must add to this carbon over here. It is the most substituted carbon. This one over here is effectively, you would have a tertiary carbocation versus a secondary over here. So this is the most substituted. The water is definitely, without a doubt, going to be coming in from behind this bond over here in a kind of SN2 type of reaction. And it doesn't want to come to this side. So that's going to cause our stereochemistry to evolve over here. It's coming in from underneath. And so in the product, it's easy to see that the bromine ends up, because this bond didn't break over here. We're going to break this bond. So this bond didn't break. So we got the bromine over here. This one is where things are going to be a little bit tricky, because remember, the water had to come in from underneath. So because it came in from underneath, it's going to be pointing down like that. I'm going to put the OH2 because technically that's what it is. And that means that the methyl group that was pointing down is now pointing up like that. I'm going to write a CH3 just to make it explicit. So once the nucleophile comes in, so we can just color all these things in again, we can lose this proton over here in the next step, so that the final product over here would look like this, and we would get this product formed over there. So after loss of the proton. So this is what would have happened. Now think about this is really the only diastereomer that could form in this reaction. Notice I've used my words very carefully there, the only diastereomer. We started with no stereochemistry. We've introduced two new chiral centers, and I want you to go and look at all the possible stereoisomers that are possible in this reaction. In other words, all the different combinations of whether this is up or down, or whether this is up or down, or this is up or down, they have to obviously be opposite to each other. And what we need to remember, though, is that this is the only diastereomer. There is the other enantiomer to this that I've drawn that is possible. That's where the bromine was at the bottom face, and that's a good thing to start with. Draw the example where the bromine was pointing down, and the nucleophile had to come in from the top face, and you'll see you should end up with the other enantiomer to this. So this is a racemic product, but it is one diastereomer. What we never get in this over here is where the bromine is down and the OH is pointing up. That will not happen. Or whether this OH is pointing up and this bromine is pointing up. It does not happen. Which is the evidence that we have for these bromoniums, that we have this, that it is an SN2 type of reaction that is occurring. And the other thing that we need to realize is that the opening of that bromonium, and remember, is that it is regioselective. And so it really only wants to go to this side, not to the other side. There will be a side product, a minor product that forms when it goes to the wrong place, but that is a minor product. It is not the major product in this reaction.